Welcome to Get Educare. In this video, I will explain the construction of transformer. If you missed the construction of transformer of part 1 class, please go through that video. In this video, I am also giving the link. Based on the construction, transformer can be classified into two categories. Number 1, core type transformer. Number 2, shell type transformer. First, we will start core type transformer. As we have explained earlier, this is the core of the transformer. This portion is called yoke and this is called leg or limb. Now, in the transformer, there are two windings. Suppose this is a 200 volt by 500 volt transformer. This is the LV winding, 200 is the LV winding and 500 is the HV winding. And the LV winding has N1 is the 200 number of turns and HV winding has N2 equal to 500 number of turns. Now, this 200 number of turns will be wound one of the leg. Suppose here 200 number of turns will be 200 number of turns N1 will be wound here, and in this leg there are 500 number of turns, more number of turns, that is equal to 500, N2 equal to 500 number of turns. But in practical, we do not do this. Why? What we do? The LV has 200 number of turns. N1 is the 200 number of turns. What we do? We do N1 by 2, that is the 100 number of turns. Similarly, N2 is the 500 number of turns. And N2 by 2 equal to 250 number of turns. So, in this leg, in the left leg, we wound how many? 100 number of turns. 100 number of turns. And around this leg, there are 100 number of turns. This is N1 by 2, this is N1 by 2, this is N1 by 2. Now these two windings are then connected in series and two terminals are come outside. This is the your LV winding. So this is 100 plus 100, that is equal to 200. Here 100 plus 100, 100 plus 100 equal to 200 number of turns. Similarly, high voltage has 500 number of turns. 500 divided by 2, 250. That is 250 plus 250. 250 plus 250, that is equal to 500 number of turns. That means in this leg over the LV winding, there are 250 number of HV winding. Here again 250 number of HV winding, and these two HV winding are connected in series and two terminal is coming outside. This is the HV winding. Now here this is N2 by 2 and this is N2 by 2. If we see the cross section view of the core with winding, then this is the core. Over core there are N1 number of N1 by 2 number of LV winding. Here N1, this is the your LV winding and it has N1 by 2 number of turns. Similarly, in this leg, over the core, there are N1 by 2 number of turns. This is again half of LV winding and it has again N1 by 2 number of turns. Over the LV winding, there is high voltage winding, HV winding, and it has in this leg, this is high voltage winding. In this leg, there are N2 by 2 number of turns, and again over this low voltage winding, there are again N2 by 2 number of HV winding. There are N2 by 2 number of HV winding. Okay. Whenever winding is placed, there is a potential difference. The core has a zero potential, suppose 0 voltage, and LV has a 200 number of turns and LV it is a 200 volt, or there HV has a 500 volt potential difference. There is a potential difference. So there will be insulation between the core and LV winding. There is a insulation between LV and HV. Similarly here, there is insulation between the core and LV, between the LV and HV. There will be insulation between here also core and LV, again LV between LV and HV, core and LV between LV and HV. Now the question arises, why we use this configuration? Why do not use in this configuration? Now whenever the reason is that whenever the current is drawn from the supply, that is called magnetizing current, a flux will be produced which passes through the core of the magnetic material. Now the flux which is linked both LV winding and HV winding, this flux is called phi m, mutual flux or useful flux. This flux is responsible for induced EMF E1 in LV winding and E2 at HV winding. Besides this, there are some amount of flux will be produced in the LV winding but come to the air and again returns back to the LV winding. Again, whenever current passes through the HV winding, a flux will be produced. This flux comes outside of air and returns back to the HV winding. The flux which link only HV LV winding or HV winding but not the both, this is called leakage flux. Leakage flux. This leakage flux don't have any contribution on EMF induced on here, and this leakage flux has don't contribution of induced EMF at here. Therefore, this is the wastage of flux. We want to reduce the leakage flux as minimum as possible. Here leakage flux is very much high amount of leakage flux. But here whenever the flux, this is the mutual flux which is passes through the core, link with both LV and HV winding, that is your mutual flux phi of n. And whenever the leakage flux come here LV winding, over LV winding there is a HV winding, this is also a mutual flux phi m. The leakage flux is this is the leakage flux phi of L, and the amount of leakage flux is less in this configuration. Therefore, we use this type of configuration of core type transformer. Therefore, this type of winding is called interleaved nature of winding. Interleaved nature of winding is used to reduce leakage flux. As a electrical or electronics engineer, we should clear one concept. Suppose this is a conductor. The current passing through the conductor is 5 ampere, and there is another conductor, but the current passing through the conductor is 60 ampere. Now what is the difference? Now the conductor with higher rating of current should have higher diameter. If the diameter of this conductor is D1 and the diameter of the conductor is D2, then D2 greater than D1. That higher the current rating, higher the cross section area of the conductor. We can say the current rating of conductor decided by the cross section area of the conductor. Next, suppose this is a conductor. The voltage potential difference of this conductor and between the earth is 200 volt, and another conductor of voltage is 6.6 kV volt. Now what is the difference? Now higher the voltage rating, we require more insulation around the conductor. We required more insulation. Here we required less amount of insulation. Therefore, the insulation required for conductor decided by the voltage rating of the conductor. Now, in core type transformer, generally low voltage side winding is placed nearer to the core, and over low voltage side we place the high voltage side. Why we do this? Suppose this is the core, this is the low voltage winding, this is the high voltage winding, and this low voltage winding is 200 volt and this is the 500 volt. But if we do the reverse, this is the core, the high voltage winding has 500 volt and the low voltage has the 200 volt. Here the core is 0 volt, the potential of core is 0 volt. Therefore, the insulating material 0 to 500, huge amount of potential difference. Therefore, the insulating material required in this configuration will be more. But here 0 to 200 volt, we required less amount of insulating material. Again, if we place low voltage winding nearer to the core, we required less insulating material. Okay. Advantages: number 1, required less insulating materials. Number 2, the high voltage winding has the current I2 and low voltage winding current is I1. Suppose this is I2, this is the I1. Now here I2 will be less than I1. Since here voltage is more, current will be less. I2 will be less than I1. Due to less amount of current, the conductor size will be less. In high voltage size, conductor size will be less. D2, here D1. D2 will be less than D1. Since the if we place high voltage side outside, the conductor size will be less. Therefore, we required less copper material. We required less copper material. insulation material required will be less, copper material will be required less. Therefore, the size, weight and cost of the transformer will be decreased. Next point, the high voltage winding has more number of turns. This is the high voltage. The low voltage winding has less number of turns. If we placed high voltage winding outside, then the tapping will be very easily provided. But if we provide the low voltage winding outside, we cannot provide tapping very easily. The tapping point will be very near to each other. Yet there will be difference between the tapping point. So next point is the it can be easily place tapping point at high voltage side. Tapping point can be placed in HB side easily if it is outside. Okay, thank you. I am sure that your concept on co-type transformer has been cleared after watching my video. Please watch all of my videos, share it and subscribe my channel so that you don't miss any important videos. Thank you once again.